was not bright enough to pick up everything in 1 week, so we're going to drop the machine learning. But it was so good to get my hands dirty and actually try to, train some networks. That was very, very helpful. The hands-on session that Marlon ran was very helpful. And therefore, that's another reason why I want to keep that we decided to keep it quick. Most of you, I assume, know about EGM, right? The endogenous grid point methods. Can we have a show of hands? I'll go very quickly through the standard one, just to bring everybody on the same page, and then talk a little bit more about the discrete choice version, and then talk a little bit more about the multidimensional generalizations, and then pose some questions. The questions that machine learning community should, or maybe we have already solved, I don't really know, but should kind of think about, and that's something that Bertil and I couldn't do in a week. All right, so I'm going to skip a bunch of slides here, but the slides are online. We are interested in discrete and continuous choices in general, but the plan for this talk, when it kind of takes the full time, is to go through the original EGM with continuous choice only. And by the way, yeah, you should think of this as a joke model, right? This is so simple compared to like everything that you've seen during the week. And yet, it works so well. It's so cool. It just flies, right? It's very accurate. So why not kind of know? Oh, wait, you already know. As many of you have done it with discrete choices? Okay, a fair bit of people too. Okay, so I guess I'll go quite fast. Oh, and I'll show you some code, although we are kind of working on the wrong tree. All right, so the original idea is the EGM and the DSE EGM without the taste shocks, and then the smooth version that we published a few years ago, and then some words on the multidimensional generalizations. So as you know, this is a wonderful idea. Let me just jump into it. This is a wonderful idea that we thank Chris for. In the famous paper, which is here, right, the Economics Letters in 2006. If I set up the model to think about it, this is extremely simple model with consumption savings. You have beginning of period wealth, utility of consumption, the continuation value, and this one doesn't have income. We want to look at the deepest model, which does, right? So once you have this potentially stochastic income, it's becoming much harder to solve. Okay. Do we all remember the steps of the EGM algorithm? And I like to present it is first as a steps, right? This is an iterative procedure. We're going backwards. We may have some known solution in the finite time period. If it's a finite horizon model, we may have some initial guess for the policy function. If it's an infinite horizon, and we're going backwards in time, right? This is a backwards procedure. Now, I like to say that we take kind of a guess of A, which we think of as the current period savings, the end of period wealth, which is also a post-decision state variable from some grid. And intertemporal budget constraint gives us the value for the next period wealth. Given the policy function that we know from the previous iteration of our backwards induction, we calculate the optimal consumption value and plug it into the early equation. And most of the times, the early equation is invertible if you have a marginal utility function that is invertible itself. And then, given that we've calculated the optimal consumption level in time period t and current time period, we can put that together with the value that we started with to recover the endogenous points in the wealth grid. Have you seen this representations though? So I'd like to think of this method as just a method defining a parametric curve. So we have the early equation, and then we use the early equation to essentially define a curve in the space, a map from M to C, right, where A is just a parameter. So by plugging different values of A into these two equations, we are recovering the pairs of M and C, right, which together form the optimal policy. Okay, So that's a neat way to think about the endogenous grid point. You impose an exogenous grid point on the post-decision state, and then you use the structure of the first order conditions in order to recover these pairs of numbers. And these are exactly the pairs that form the policy function. How does it go? Well, this is just the inversion of the earlier equation that we can calculate all conditional on A, right? And then this is the value that we've recovered plus that initial post-decision state that forms the endogenous beginning of the period state. Okay. And so from this, we can actually think of what are the assumptions that are needed for this method to work well. Where are they? There. So A1 is strictly concave monotone indifferent differentiable utility function. We want that to be able to invert the marginal utility, right? Okay, and do it analytically, that's the hope. And then we are golden, then we don't have to run any iterative procedures. We're just essentially reconstructing this parametric curve. Yeah, in this classical formulation, there's a single continuous state variable MT, right? Single continuous choice variable. And then another thing which is quite important is this transition probabilities of any additional states are independent of MT. So in fact, what is this post-decision state that enables the endogenous grid point method? That's something that serves as a sufficient statistic post-decision of everything that happened before. So the reason that we can actually run endogenous grid point method is that we can, in the problem, we have this end of period wealth, right? Something after the consumption has happened that characterizes whatever happens in the future. In other words, it is a sufficient statistic for everything that happened in the past. And that's kind of the key feature of the model that you require in order to run this wonderful non-iterative procedure. Okay? Did I lose you, or this is just too easy? Yeah.
So I'm thinking about the condition 3.
Yeah.
So if you consider like retirement status is one state variable discrete, but the retirement status would be dependent on MT asset. So I wonder whether your classical model is including those kind of.
So are you thinking of retirement as choice?
Yeah.
Okay. This is going to have only single choice. But imagine that you have, I don't know, income process, which is exogenously evolving without any additional choices. That's what I think of this additional. Additional means exogenous in some sense. Could be Markov state variables, but the condition is that the transition probabilities for this states cannot depend on something that you haven't recovered yet in the EGM step. Cannot depend on anything other than the post-decision state that is in the consumption savings model, the wealth in the end of the period. Okay. Why is that? Well, again, if we just go through the steps of the algorithm, you know, let me just, you know, we start the algorithm here, and then we, you know, the structure of the intertemporal budget constraint usually is such that A is a sufficient statistic for the wealth tomorrow. But here we need to calculate this expectation in general case. The expectation of the marginal utility of consumption next period depends on the transitions of all the states. And therefore, if you want to include other states into the model, that this expectation has to be computable, conditional only on A and nothing else. Okay. Questions? No. So I've done something wrong. But everybody had, well, most of the people had seen it before. So let me continue. Yes, question.
Is there like some rule of thumb actually which variables we should optimally interpolate for this procedure, right? You can interpolate either on consumptions or on saving and then back one from the other. And
yeah, okay.
Typically find savings to be more linear.
So yeah, so we're interpolating this object here, right? We approximate the optimal policy function with the set of endogenous grid points and have to interpolate it. And there is no specific rule connected to EGM. well, I guess I have to be careful about that. Well, let me come back to that. But in general, the rule is that you want to interpolate the objects which are linear. You want to transform the object if you know how, if you know about the nature of nonlinearity of that object. It's like unwrapping that piece of the sheet of paper that Jesus showed to us. You want to unwrap the nonlinearities and interpolate something which is closer to being linear. That's generally the same.
So I've never thought about this, but what if EGM would break if you had a 2-asset problem, right? If you were choosing 2 assets for the next period.
So this is towards the end of the lecture. So I want to talk about multidimensional versions, and this is hard. It will generally be much harder and possibly break. Okay. All right. So when you think EGM, think of this parametric curve. That's really what we're doing mathematically. We're going through the grid, exogenous grid on some sufficient statistic, and using the first order conditions, we are recovering the optimal policy on an endogenous, what happens to be an endogenous grid in a state space. The benefit is clear, right? There are no equations, no maximization, nothing. You just basically choose a grid on A and compute your policy. That's in every time iteration. And then as you have to take a step back, then you take a step back and interpolate over the next period also. I should stop in about 25 minutes to give time to. All right, you all know that it's very quick and it's not hard at all. Here's the 11th line implementation in MATLAB. This is a full-blown life cycle. Life cycle doesn't matter. Full-blown dynamic stochastic consumption savings model. I wanted to run some code. And so there are 2 sets of codes in the repository. There is some MATLAB code, which I'll run now, and there are notebooks in Python. We started working on this when we were doing MATLAB. I'm just going to run this run file, run DSE. And what it's doing is actually solving, it's running VFI, right? It's solving the consumption savings problem with VFI. And each dot here corresponds to the point in the state space. The time horizon was only 25. This is finite horizon problem. And it took some time. I'm not going to run it again. But you can see that it's not that quick as you know. And EGM is also, what is that? I want to run it here.
Fedor, maybe go back with to the module.
Did we change the module here? Oh no. Okay, well, you will be happy to know that this is something which is modified.
Model D2.
And the discard changes, and the code in the repository is clean. All right, yeah. Okay, so EGM also draws dots, but these dots correspond to 100 times solved model instead of 1.1 in one time period. And so here, what was the average? If I scroll up, and we see that this is done in about 4.4 seconds on a particular hardware. You have to take these numbers with a grain of salt. They are actually random numbers, right? We have to do a study if we want to look at numbers, but just the magnitudes. I mean, this is 2 over 1,000th of a second. Point being that you can solve this particular problem so many times in so many different situations. If you need to solve it, I don't know, heterogeneous agents or estimation, iterative procedures, equilibrium. It's just so fast that if the problem fits into this framework, I don't know why you wouldn't do it. In fact, I was thinking that you can have a neural network train on some complicated equilibrium relationships, and inside of your cost function, you could solve you could run EGM with no time lost to produce the optimal policy for stochastic consumption savings model, if you need that for your for your cost calculation and train the network on something higher level. All right, going back, accuracy of this method is also going to be very high, right? Because by definition, it satisfies the earlier equation in the set of points where we are recovering, which we're recovering. Of course, it depends on the interpolation method, you know, how well it does in between those points. But again, thanks to Chris, we have a method of moderation which shows you how to bound the solution of this problem between two linear solutions, which can be approximated infinitely accurately. And that means that, you know, the solution of your particular problem can also be approximated very accurately given the linear solutions, right? And then the number of grid points can go down or the accuracy can go up. All right. A couple of words about the credit constraints, right? This happens to work really, really well with the standard credit constraints. And the relevant picture is this. And this is actually an important point. The way EGM runs, right? The right way to do it is to start with zero savings. So assuming that there is no savings going to the next time period, and that recovers this exact point. That's the point where the credit constraints essentially stop binding, right? This is the point where it's optimal. Remember, this is going to have the endogenous value of wealth. On the horizontal axis here, I have wealth. And this is the optimal consumption function. And then as it becomes optimal to save something, then you have this optimal consumption function separate from the 45-degree line. But then you can show that in standard, under standard assumptions on the utility and the preferences, you have to stay on the 45-degree line between 0 and this point, right? Nothing new here, I guess. But the point is that now we can recover this kink extremely accurately.
Perfectly.
No other method. I mean, you have to be extremely lucky to somehow put a point there in any other method which works off the grid, either regular or stochastic on a state space. Right? Is that clear? So in regular grid, you would put a grid on wealth on your state space, or maybe you simulate some points in the state space, and this point will probably be smoothed out somehow. Of course, in the limits, it should be not important. Right now, before I go to the EGM with discrete choices, let me run a test. Right. So what is this test? We're going to be simulating consumption paths in a very standard way, just starting at some level of wealth and then applying policy function over and over again. So I want to simulate consumption paths in the model where you can see, well, maybe I can make it larger actually. Do this. So this is going to be the model where the discount factor will be exactly offset by the interest. And this is a deterministic model up to now. So we didn't have any expectations there. What should we observe with this restriction on the consumption savings model? Yeah.
Consumption's flat.
Absolutely flat, right? This is an exact result for perfect consumption smoothing. So if we simulate a consumption path, we should observe a flat line. And so let me run this one here. And so I guess I want to solve with VFI first. Just for illustration. And yeah, we have to wait for a little bit. And that's probably not a very good implementation anyways. It does converge, that's the main thing about VFI. So here are your two consumption paths over this 25 years of life. This is now time, right, ages. And we started the simulation at some points, a couple of points. I mean, you can say I'm cheating because I'm showing you 2 points. Because of course, if there's only one line, it would be jiggling a little bit by MATLAB set automatically adjusting the minuses, the limits. This is between 6.4 and 7 in some metric. I think the maximum wealth that I'm using here is 10. But you can see that, you know, this is consumption. People underconsume, and at some point they start catching up, and then, you know, they're completely out of balance. This is the simulation that should produce a flat line. It's a really hard test. In fact, if you've seen Michael Keane talking about the art of structural estimation, he makes this into a little story when somebody would come to him and say, you know, I got it, I solved it right. The consumption paths are nearly flat, you know, they're almost flat. And then I would hear, you know, no, you got a bug, go back and make sure they're completely flat. And then I believe in your EGM method. And so this is the example when they're not, right? And the example, I mean, what we get with EGM is this picture. And that's what made my team happy. And that's the illustration of the fact that, I mean, where's the error coming from? Why is the test complicated? That's clear, right? Because small errors along the life cycle simulation accumulate, and then you get out of whack. And then you get something like that towards the end. Where are these small errors coming from? I mean, you can run VFI with quite dense grid, and that's probably all doable given the computers. Well, my understanding, my primary idea and investigation shows that it comes from smoothing this particular thing. So once you have a little bit of inaccuracy around here, and where is it located? It's located approximately at the level of your per period income, right? That's, if you think about it, it's up to about your annual income that you can consume everything, because you'll get this amount next period in this model for sure. Okay, DSE2023. So what do we want here? So first we want to set up a different model, right? So this model has a discrete choice, and it's the simplest model with discrete choice. It's a retirement model, and I'm going to have retiree, second state variable, which denotes whether an agent is retired or not retired yet. We will keep retired people simple, right? Retirement is absorbing, and all they do is consume and save. We've already solved this problem. Now, is this absorption important? No, it's not important. You could have retirement people also having a discrete choice. I just want to talk about workers having a discrete choice and not think about retirees that much. Now, workers have discrete choice, which is between staying working or going on to retirement. And these are two lines in this Bellman under the max sign. One line is essentially a consumption savings problem that we've seen before, and that's the same problem that retirees have. Another problem is the problem with income, right? So if you're working, then you have some income. Everything else is the same, right? We have the standard theory utility function. This problem can be solved analytically. Thanks to John, we have this picture and this formula here. You know, you have to have sufficient patience to go through all these cases. But what happens is that the optimal consumption function is discontinuous. I will try to explain carefully why that happens. That's one feature. And you can see that the capital T minus 2, this green optimal consumption function, is close to the terminal period, T. And as you move away from the terminal period T, then you have accumulation of these discontinuities. And this is the exact solution of the problem that I just had on the book. Okay, so what happens? I mean, this is a bit of a slide of what we want to do. We want to avoid solving equations still, right? And so we're going to be doing EGM step conditional on the discrete choice. How it goes? Well, now we also have to calculate value functions, which is possible. A question?
This is connected to what you mentioned previously about neural nets. So because of this discontinuity, so this is the main problem. I mean,
yeah, this is like the first sign that there might be problems.
okay.
So suddenly we have a problem. It is solved, isn't it right, Simon? I think discrete choice is solved, but you know, it's nice to see in neural nets. Yeah, I think Lilia has a paper. Yeah. So you can talk to Lilia about how to do a discrete choice with neural nets. But it's very useful to understand the underlying problems. So this is the problem. I mean, you have to realize that you may be approximating something pretty nasty. Okay, so what do? We are calculating value functions for the worker for two different discrete choices, retirement and keeping working. And this is the terminal period. We set up the timing in the problem such that wage comes the next period. And this is assumption which is not that important really, but it has implications for the last time period, because nobody wants to work here, because there's not going to be a wage for this work, just this utility of work. And therefore, if you compare value functions, they're drawn over the level of wealth. Oh, and by the way, another point I guess that I forgot to make about EGM is that this state space we're treating in a completely continuous way. We're not discretizing, or we allow the discrete points on which we approximate the policy functions to fall anywhere. Anyway, back to this picture. Nobody wants to work in the last period because there's not going to be any wage. But if we go to capital T minus 1, then because there's, on one hand, there's wage for work, but on the other hand, there's this utility of working, there's this trade-off, and there will be a sweet spot, this threshold here, on one side of which you want to be a retiree if you have enough money, and on the other side you want to be a worker. Okay, if we zoom in into that intersection point, where is the true value function now? Well, you're maximizing value, right? Remember the Bellman equation, you're taking max over two options. The value will be the upper envelope between these two choice-specific value functions. Once you have an upper envelope, you will have a kink. So John, I think, mentioned this by saying that the max tends to make things convex. This introduces some convexity into otherwise concave value function and makes it essentially non-convex, right? We are in the situation where the first order conditions are not sufficient anymore. All right, wonderful. If we calculate the optimal consumption, then we will see this picture. And here, forget about this vertical line, it shouldn't be there. But it turns out that if you're a worker, you don't have enough wealth to retire, you want to work, this is your optimal consumption policy that corresponds to your state of being working. If you are retiring, then this is your best choice of consumption. And there's this discontinuity that corresponds to that kink in the value function. So what we have is that these specific value functions intersect. We have to take the upper envelope according to the Bellman equation, and that introduces the kink, the discontinuity in the optimal consumption function. That explains those discontinuities that you've already seen in the analytical solution. All right, but then it goes even more interesting. And so the story here is that we've been working some years ago on this with Bertel, and we thought that, oh, we cracked it, right? This is all you have to do, and just take an upper envelope and you're done. But then we went to, then you look at what happens at capital T minus 2, and we were actually sorting the endogenous points in the grid space, and we've noticed that there's something like this. We called it a zigzag region. You zoom in and you realize that your value function is actually a correspondence. There's not a single value corresponding to different points of wealth. Okay, and this is in period T, capital T minus 2. Why is that? And what to do with this? So what happens? The upper envelope on the value function has a kink. We've already seen that. But that creates the situation when the first order condition is not sufficient anymore. And so as we are doing the EGM, machinery EGM steps, suddenly there are these solutions that correspond, that solve the early equation, but do not maximize the value. Right? That's essentially what happened here. So we have some solutions of the early equation which don't maximize the value function, and we have to do something with that. Well, you have a question?
Just an intuition for that. It's that you solve for a value of the in the period state that you would never voluntarily have chosen. And so that's why the value function of the other thing is higher. that's the kind of intuition for why you get this. Result.
Yeah.
That you get the first order condition for the problem that you would never have solved, you would never have done to begin with.
I have an early equation, okay, somewhere later
So
to,
that's
I
a
think,
good
support this intuition. But, okay, this is what actually happens, right? The early equation has a discontinuity, and as you go through through different values of wealth, not in the algorithm, but kind of investigating what happened, it turns out that the earlier equation has multiple solutions corresponding to the same value of wealth. And, what do we do with that? Well, if we just look at what EGM step produces, it's like, this is wealth again, an endogenous grid. The value grows, and then at some point kind of jumps back, and then creates this region corresponding to the interval where the value correspondence appears. And the solution is to run an upper envelope again, right? Just maximize the value. That's very natural. We have Bellman equation. Okay, we can't use the first order conditions, but we always have the Bellman equation.
Okay, quick question. Assume we have like a model with a discrete choice. We, I don't know, maybe naively do EGM and don't get these kind of non-monotone endogenous grid. Does it mean there's like no problem, and like, I don't know, for this specific type
Yes.
of problem, we could just, that could be a
That's
different
right.
solution?
So even with discrete choices, it could be that the model is smoothed out by additional randomness that is inherited in the model. We will come to that. It could in principle be that, the secondary kinks don't appear because of the smoothness of your problem. So this needs to be diagnosed and acted upon, but doesn't appear necessarily. Okay, let me speed up a little bit. The bottom line is that you have primary kinks. These are the kinks in the value function that corresponds to that exact point where people are indifferent between discrete choices. And then you have what we call secondary kinks, which are like images, echo of the primary kinks sometime in the future. They really exist. They're a real problem in the deterministic world, because, if you're here in terms of wealth, due to the deterministic solution, that you will be exactly at the kink in the next time period, and therefore this kink appears. Now, what happens if we have stochasticity somewhere in the model? Then these are, so what did we do here? We introduced random returns.
Mhm.
Once you introduce random returns and you vary the scale of that shock, then you see that the secondary kinks start to disappear. There are two troubles. First trouble is that you don't really know how much randomness is enough to convexify the problem. And the second thing is that this primary kink, where you're indifferent between discrete choices, cannot go anywhere. Because this is all, if you have a discrete choice in the problem, then there will be a kink corresponding to switching between the discrete choices and the corresponding discontinuity. So this only has to do with propagation of the kinks in the backwards induction, in this time induction. Oh, going back to time. Okay, what can we do? Well, we can use the discrete choice theory, right? This wonderful T-shirts that students in Copenhagen gave to many of us. Extreme value is the new normal. We have to rewrite the problem. What's the idea? The idea is now that instead of choosing either or, we can smooth that choice a little bit by introducing some taste shock, right? And convert the problem of, being an indicator, you're whether worker or retiree. We convert this into a smooth problem where you have a choice probability of becoming a worker, or becoming a retiree, or staying a worker. And that requires you to rewrite everything, and then we transfer the problem now into the domain of choice-specific value functions, right? So now I have two variables in the state space, and the choice, this in red, this is a choice of a worker to remain a worker, and the choice of a worker to retire. And there are different equations, but this is all because we will now have this scale taste shock added to the choice-specific deterministic values. And now we are solving in the space of these deterministic values. Deterministic choice specific value functions. And once we reach the fixed point, or well, in finite horizon, there's no fixed point, just a direct calculation, then we can plug them into the choice probabilities here. right? That's all the standard theory. This is going back to an FXP. Now, what happens with all our kings? We can understand that by looking at the early equation. It turns out that the earlier equation, these are early residuals for different levels of consumption and a fixed level of wealth. It turns out that these secondary kings start to be, I'm sorry, the early equation becomes smooth. This is talking about the secondary king because the value function is still non-convex in general, but there is no king in the value function. And therefore, the early equation, which used to have a discontinuity like this dashed line, now has a smooth transition between different solutions, different zeros. And that's even worse, right? Because now we may have 3 solutions instead of 2. And in some sense, oh, we don't have that other picture. But if you have enough of these shocks, then then it can be convexified completely, right? And just one solution remaining. This S shape could be crossing the zero line just once. Okay, so that's the idea. The idea is to smooth out the problem, and that takes away the problem of this primary king by transferring this whole decision process into the probabilistic space. And it also allows to, it kind of moderates the accumulation of kings in the time backwards induction. Now, if you don't like taste shocks, then there's an approximation, the extreme value homotopy theorem, which says that you could use that as just numerical noise to smooth out the problem. And by changing the sigma, the scale of this shock, you can approximate the deterministic setting as closely as you wish. Okay, so I promised to talk a little bit about the generalizations. Let me run this test, maybe just one more run. What happens if we have a retirement problem, which is deterministic? Simulated consumption path, and we want to simulate a consumption path in the problem with discrete choice, right? Where the same restriction applies, where we would expect to have perfect smoothing, and that's your answer. Okay, so this speaks to the accuracy of now DSE2023, where this dashed lines corresponds to the point in their life cycles of these people where they switch from being a worker to being a retiree. How is this possible, you may ask? How is it possible that they smooth consumption over their entire life cycle, taking into account retirement so well? Well, they are hyper-rational. Remember that solution with lots of discontinuities in the optimal policy function? Well, these people, they are so rational, they can foresee all these kinks, and they can position themselves by changing their consumption such that they jump from one little continuous section of that policy function to the other one in the life cycle, right? So across all different solutions in such a perfect way that the resulting simulated consumption path is exactly flat. All right. So what happens if we think about multiple continuous choices or multiple continuous variables? I mean, adding discrete choice gives you a lot already. If you have a problem with multiple choices and maybe multiple state variables, you could discretize one of the choices, for example, right? But can we do better? And so the first, I think the first attempt on this was by Jesus as well. In 2007, what they did is that they used the idea that they can run EGM with respect to one choice and then kind of discretize the other choice, so VFI for the other choice. The overhead here is to transfer the problem between these two formulations. And so, I mean, it just happened to work because the choice that was left for the VFI was kind of simple in some sense. It didn't require a lot of iterations. Now, the real problem here is multidimensional interpolation on irregular grids. And this is what Ludwig and Sean explored in their paper. The essence that, it would be nice for you to grasp is that if you have multiple dimensions of the state space and you're doing some sort of EGM, you will end up with a grid that looks like that. irregular grids are hard because in order to properly interpolate on them, we need Delaunay triangulation. And that is just slow.
You don't actually.
Yeah, let's get to this. That's next slide.
Oh, good.
Now, Matt White, Chris's student, came up with this idea. You know, what do we have? We have this nonlinear square or rectangles, right? What's the right word here? And in principle, if you know enough about the structure of them, then you can have a continuous one-to-one mapping to
Quadrilateral.
quadrilateral. So here's the idea is to kind of do, again, like unwrapping the sheet of paper. You have something nasty that you have to work with, and you kind of twist it and stretch it to get a rectangle or to get a square, and then map back the interpolated points. As far as I understand, you have to know enough about the structure of your problem.
Yeah, well, it just needs to be fun. We have this in the Econometric toolkit, by the way.
All right. So another paper that I want to mention is by Jeppe Drødal and Thomas Jørgensen at Copenhagen. Their idea is that you can actually allow all sorts of binding constraints into the problem and discrete choices, which is kind of like a sort of a binding constraint, and then solve using EGM conditional on this different, what they call segments. A segment is a combination of different constraints that fixes some of the choice variables and leaves some of the choice variables to be determined. You know, when it's all done, all this conditional EGM calculation, you end up with surfaces of different, different segments which are partially overlapping, but maybe not completely overlapping. And their approach is to recalculate everything on the regular grid and just run maximums over these different segments to calculate the upper envelope. And the upper envelope is, of course, what you need to do in any case if you have any source of this convexities in the problem. Now, this is what they get in the problem of consumption and savings, and I think an additional continuous state of pension funds, right? So two different types of savings and consumption. This is the consumption function on the space of these two continuous state variables. You can see it's very discontinuous. And again, this poses the question of how to do it using neural nets and whether objects like this can be properly, and we need to learn more. And that's next period pension wealth on the same space. Okay, I'm going to stop here. Some other papers listed there talk about what is that exact class of models where this can be useful, because the takeaway message is that, if your problem somehow fits into this endogenous grid point framework, then it's very, very useful to at least know about these tools. And I think, we can all find ways to combine these with the very powerful high-dimensional solution methods that we learned about this week.
Just one real comment.